All right, today we're going to talk about related rates. But to understand related rates, let's just dive into this first example. In this example, a pebble is dropped into a pond and it causes ripples to form in concentric circles. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. Then it says when the radius is 4 feet, at what rate is the total area of the disturbed water changing? Okay, and then you probably remember this, but we're given that the area of a circle is pi r squared. All right, so in this example, we have, we're told that the radius is increasing at 1 foot per second, right? So radius is a function of time, right? And it's changing, right? The radius is changing over time. And the radius is related to the area of the disturbed water, right? So we have these related rates. We know the rate at which the radius is increasing, and what we want to know is the rate at which the area of the disturbed water is changing. Okay, these are called related rates. Okay, so in both R and A are functions of time. So we're going to consider both R and A to be functions of time. So I've just read the problem carefully, and the next thing I'm going to do is I'm going to make a sketch. All right, so I'm going to draw a circle. Right, I'm just going to draw a circle because I know I want to know how the area of this circle basically is changing as the radius is changing. All right, so this circle has some radius r, and what are we given? We're given that the dr dt, right, is equal to what? 1 foot per second. Okay, we're given that that rate of change of r with respect to t, right? It's increasing at 1 foot per second. That's dr dt. And we want to know what's happening with we want to know the area, how the area is changing when at a particular point, right? When the radius is 4 feet. Now the area is equal to pi r squared, and what we want to find, the dA dt. Okay, so we're just considering both the radius and the area to be functions of time. All right, so we've written the relationship between area and the radius, and now if we just differentiate both sides of this equation, what do we get? We're going to get dA dt is equal to, all right, we're going to use the chain rule on this. All right, now pi is just a constant, so I'm just going to bring down the 2. I get 2 pi r, but keep in mind that r is a function of time, so we're going to use the chain rule on this. dr dt. Okay, so both a and r are functions of time. All right, so now we're going to take what we're given, and we're going to find the dA dt. So we want to find how the area is changing over time when the radius is 4 feet. So we're going to plug in the radius of 4, and we're told that the radius is increasing at a rate of 1 foot per second. Okay, so that's my dr dt. Now I can just calculate it, and I get 8 pi feet per second. Sorry, square feet per second, right? Because it's area now, right? It's the rate at which area is changing over time. So the units are going to be square feet per second. Okay? Now, the last thing you should do is just kind of make sure that that makes sense. Does that make sense? And I think it does, because if the radius is increasing, the area is increasing. That's kind of the main thing. Make sure it has the correct sign. So you would expect that the area would increase, right? So it's positive. The dA dt is positive because the dr dt is positive. Okay, now I could calculate this. If I took 8 times, I could get a better number. This is the exact value, but if I take 8 times what, pi, that gives me, I could write this as 25.13. I'll just round it to 2 decimal places. Feet per second. Square feet per second, I should say. Square feet per second. All right, and that's your first related rates problem. Now, there's a summary of, kind of a step-by-step summary of how to approach these problems down here. So you can refer back to it if you need to. So I will meet you in the next video for the next example.